This is Group 2's tolerancing scenario project consisting of Julian, Adrian, Oria, and Andrew. We decided to use an Apple box as our tolerancing scenario project. This is because recently luxury tech companies have been putting a large emphasis on quality throughout the product lifecycle to win over consumers. Apple is a great example of this as they take the idea of quality to the next level by starting from the beginning of the user experience, the unboxing. Apple happens to be an amazing reputation for the amount of effort they put into the packaging. You've likely heard or experienced the air cushion effect when closing or opening an Apple package. This effect is a testament to the amount of engineering that goes into the packaging, which is a complex paper product. We hope to replicate what GD&T features they employed to maintain the size, form, and orientation of each product leaving the factory floor. We first considered what features were most important for such a product. We concluded that size and orientation were very important in the design. We found that the perpendicularity of the sidewalls and the flatness of the top and bottom faces were the most important. Once that was determined, we saw that we needed to control the size, form, and orientation of the design. We decided the best way to estimate what tolerances that were achieved was to do some measurements on the physical system. Since this box would have successfully met Apple's tolerancing requirements, now that it's in the hands of the consumer, we can assume that these ranges to be within reason. And the most important part was that these tolerances achieve the satisfying air cushion effect. As mentioned before, our mating parts consist of the bottom base and the top lid of the box. Shown is the drawing of our Apple box's bottom base. Our GD&T is defined through the side of the box, since the main mating surface when the two parts are fitted together. This is a size feature to control the allowable width of the box base. The upper and lower boundaries are 0 and negative 0.8 millimeters, which control the largest and smallest width allowable. The upper boundary is the most significant, as anything larger than 94 millimeters would cause interference issues with the lid. This is the perpendicularity constraint, which controls the orientation by referencing the established datum A, and it applies a tolerancing zone of 0.2 millimeters. This feature is important for controlling the amount of allowable slant in the exterior walls, as it is desired that these walls are perpendicular as possible. There are two features here. The first is datum feature A, which is used to control the orientation. The second is the flatness feature, which controls form, which is a slanted rectangular symbol, to a tolerance of 1 millimeter. Datum A was needed to use the perpendicularity feature for the sidewalls. The flatness feature was needed to control the mating issues that occur if the bottom face were too slanted. Shown is the drawing of our Apple box's top lid. Similar to the base, our GD&T is defined through the side of the box, since this is the main mating surface of the GD&T for the lid of the Apple box. It is very similar to the Apple box base with some major differences. The size feature has the upper and lower boundary of 0.8 millimeters and 0 millimeters, which establish the largest and smallest widths allowable. But in comparison to the base, the lower boundary is the most significant, as anything lower than 95.4 millimeters will cause interference with the bottom base. The perpendicularity feature is the same as the base. A relatively small tolerance was chosen for both to tightly limit the amount of slant. Datum A is established to be the top face of the top lid. The flatness feature control is the same as the base. Alternatively, this assembly could be toleranced by the profile callout. This would constrain both size and orientation, but the downside to this is the loss of control. By using a bilateral tolerance on the size and perpendicularity callout, we are able to tolerance the slant of the wall separate from the distance between the walls. This is lost if we were to use profile.